let's get started. Find a piece of chalk that's kind of small. That's better. Duh, it'll be at the end. Okay, so quick recap of what we covered last time. So section 2.1, the section we did last week, was on the interior and the closure of a set. So we already had a notion of open sets and closed sets in a topology. And now we want to look at A, where A is just a subset of X, and X is any topological space. All we know is that A is a subset of X. We found a set to associate with A that's always open, and we called it its interior. And we found a set to always associate with A that's always closed, and we called it its closure. And we defined them such that A is always sandwiched between them. So the interior of A is always a subset of A, is always a subset of the closure of A. So in some sense, this is the biggest open set inside of A, and this is the smallest closed set containing A. So one intuitive way to think about it is this is the closest open set we can get to A, and this is the closest closed set we can get to A, if A itself isn't open or closed. Obviously, if A is closed, it's just equal to its closure. If A is open, it's equal to its interior. But let's go back and look at their exact definitions to make sure it's all clear. So interior closure, here's our definitions. Let A be a subset of a topological space X. Remember, if I say of a topological space X, it's implied that we have a topology defined on there. I'm just not going to specify what it is. Then the interior of A, which we signify A with a circle above it, is a union of all open sets contained in A. So take all the open sets that are a subset of A, union them all up, what do you get? That's the interior of A. And since you're unioning up subsets of A, then the interior of A has to be a subset of A. Could be equal to A, but it's definitely a subset of A. So the interior of A is a union of all the open sets contained in A, and the closure of A with a line above it, is the intersection of all the closed sets containing A. It's the points that are in every single closed set containing A. So if it's a closed set containing A, A is for sure in there. So A is for sure in every closed set containing A. This is the intersection of all the closed sets containing A. This is the thing that's in every closed set containing A. And every closed set containing A obviously contains A, and therefore A is always a subset of its closure. Make sense? Mm-hmm. And then we proved in the case where A is open, it's equal to its interior, and where A is closed, it's equal to its closure. Okay. And then the big theorem last week that I told you better memorize is Theorem 2.5. It's got that special name, 2.5. So let's go over that one again and make sure that one makes sense. Feel free to stop me at any point if you have questions, as always. Okay, so Theorem 2.5. Let A be a subset of X, where X is a topological space. Then X is in the closure of A, is logically equivalent to, for every, remember when I do u sub X like that, what does that stand for?
The neighborhood of X.
A neighborhood of X. That's an open set containing X. All right? We get tired of having to specify that every time, so that's our shorthand. And I said I'd always use u sub X that way. So X is in the closure of A is logically equivalent to, for every neighborhood of X, that neighborhood of X intersects A. Their intersection is not empty. They have some point in common. Every neighborhood of X intersects A. X is in the closure of A if and only if every open set containing X intersects A at some point. Make sense? Mm-hmm. Now our intuition for this, come down and look at R2, is, so here's A. What do I have A? I'm saying A is all the points in here, not including these boundary points, including these boundary points with this weird offshoot. What's the interior of A? What's the biggest open set you can fit inside A? This is obviously an R2 with the standard topology. That is all the points inside of here, not including the boundary. The smallest, or the biggest open wall you can get in there, basically. And the closure of A is all the points inside of here, including the border and including this weird offshoot. Right? So here's what we're saying. we're saying a point is in the closure of A. So pick a point in the closure of A. And we're going to try and pick a tricky point. So we're going to try and pick a point in the closure of A that's not inside of A. Try and pick the trickiest point we can, which would be a point over here. So here's our X. We're saying a point X is in the closure of A if and only if every possible open set you can make containing that point intersects A at some point. And notice since X wasn't in A, it's not enough that that open set has X. It has something besides X, since X was one of these weird boundary points. So X is in the closure of A if and only if every possible open set you can make around that point intersects A. That's what this is saying. Feel like you got the intuition there?
Yeah.
Okay, this is a logically equivalent formulation. This is just taking the contrapositives of the implications up here to get this. So, there she is. Still just doing a review. So, the logically equivalent version of this is, instead of X being in the closure of A, it's X is not in the closure of A, is logically equivalent to, I can find some neighborhood of X such that it doesn't intersect A. So I'm saying, now if we look at the picture here, now pick a point X that isn't in the closure of A. Any point in X, or any point that's not in the closure of A, we'll pick some point there, there's X. We're saying X isn't in the closure of A is logically equivalent to, I can find some open set, there's one, containing X, I can find some neighborhood of X, I can find some open set containing X, such that that open set intersected with A is the empty set. Or in other words, they have no overlap. Their intersection is empty. They have no points in common. So these are two logically equivalent ways of thinking about the same theorem. You're going to use this theorem over and over again, so you need to get comfortable with it.
Okay.
Any questions? And that was just for our two. You get to continue?
Mm-hmm.
Okay. So now we start new material, section 2.2. Section 2.2 is all about limit points. And these are going to be limit points just like they're defined in calculus. For those of you who have taken calculus, we're talking about the same exact thing here. So let A be a subset of the topological space X. Then the point, little x and big X, is a limit point of A, provided that every neighborhood of X intersects A at a point other than X. It's a mouthful of a definition.
Can we real quick go over this intersects?
You
Just
also forgot your Y with every.
Is the limit point of every neighborhood.
what was the intersects with the AB?
Yeah, so let's look at this in R2. So in R2, looking at this exact same picture, it turns out, there's no reason for you to know this yet, but it turns out that the limit points are going to be the exact same as the closure in R2. So turns out those are going to be the same. That's not true in all topological spaces. This is just to help give you intuition for what this definition is saying. So a point, so here's our A point X is going to be a limit point if every neighborhood of X intersects A at a point other than X. So when X is over here, obviously X isn't in A, but notice that this is also a limit point. If X is here, this is a limit point because any open set you can create around that point intersects A at some point other than X, right? So that's what it's saying. Let A be a subset of the topological space X, then the point little x and big X is a limit point of A, provided that every neighborhood of X intersects A at a point other than X.
We go over intersects again, meaning
So this set I drew around X intersects A at a point other than X.
right?
There's a point right here
right.
that's in both of them, and that point's not X. So there has to be a point both in the neighborhood and in A, not counting X. You can't use X. Does Does that make sense? So let's look at another example that's not just R2. Oh. No, we're not done yet. Intersects A at a point other than X. We denote the limit points of A by A prime. So from here on out, anytime I use A prime, I'm talking about the limit points of the set A. Okay, here's another way to write it in working this notation. X is a limit point of A is logically equivalent to, for every neighborhood of X, when you take X out of that neighborhood, its intersection with A is still non-empty. So use of X intersects A at a point other than X. When we take X out of there, it still intersects A. Make sense?
Mm-hmm.
Okay, so let's do an example to help establish intuition. So let's look at 1 over n, the set 1 over n in the standard topology on R. Now, do we know what this set is?
Yeah.
1 over 1, 1 over 2, 1 over 3, 1 over 4.
Okay.
Let's draw it on the number line real quick to make sure we're seeing it. Here's 0 on the number line, here's 1 on the number line. The first point in here is 1 over 1, that's right here. The second point in here is 1/2, that's right here. The third point in here is 1/3, that's right here. 1/4 is right here. 1/5, 1/6, 1/7, 1/8, whatever. And it keeps getting closer and closer to
Yeah.
0. So, what are the limit points of this set? What are the points such that no matter how small of an open interval you place around that point, it still intersects this set? What points can I put really small intervals around and be guaranteed to intersect this set?
0.
0? Just 0?
Yeah.
0 is the only limit point of this?
Mm-hmm.
Yes. So the answer is the set containing 0.
Okay, that makes sense.
Let's roll out some points why they're not limit points. What about 1/2? Why isn't that a limit point?
Because you're using it.
Yeah, that's in A, but our limit points can be in A. In R2, all these points were limit points. That was a limit point. That was in A. This was a limit point. It wasn't in A. So just because it's in A doesn't mean it can't be a limit point.
You can make an interval small enough such that it doesn't contain 1/3 or 1, which are the two consecutive numbers by whatever.
Perfect. You understand what she's saying?
No.
She's saying, here, let's draw it out again. Here's 1. Here's 1/2. Here's 1/3. Here's 1/4. And then it continues, and the rest of the points are over here, right?
Mm-hmm.
She's saying, just pick a really small interval around 1/2. Is a small interval around 1/2 open?
Yeah.
Does it contain 1/2?
Yeah.
Yeah.
So this is a neighborhood of 1/2, right?
Okay.
Where does it intersect A?
Throughout the whole interval.
Yeah.
No. A is these points. A is this point, this point, this point, this point, this point, this point. Here's all the points in A.
Okay.
The only point where it intersects A is 1/2.
Oh, in that interval, right, of course.
Right?
Mm-hmm.
Yeah.
Okay.
Does that make sense?
A little bit.
What is A? A is a
all
point.
those points, yeah.
1, 1/2, 1/3, 1/4, 1/5, 1/6, 7, 8, 9, 10, etc.
Mm-hmm.
This open interval is all the points from here to here.
Yeah.
Right? This could have been something like 7/16 to 9/16. Some small interval around 1/2 that definitely doesn't have 1/3 in it.
Okay.
All the points inside this interval that are also in A, what's the intersection of this interval and A? Maybe that's the way to think about
1/2.
it.
Yeah, it's 1/2.
Just 1/2. So this interval does not intersect A at a point other than 1/2.
Oh.
So 1/2 can't be a limit point. In
Because-
order for it to be a limit point, then every open set containing it has to intersect A at a point other than itself. right?
Okay.
U sub x, in our case it's this open interval, minus 1/2, intersect A is empty. So it's not a limit point. This is a case where it is a limit point. The only limit point is 0. Any other point you pick, I can create such a small interval around it that it doesn't contain any other points in A.
Yeah.
Is there any other numbers you want to try and see it?
I think I got it.
Any number you're suspicious might also be a limit point that you want me to show real quick, isn't it?
I'm mostly reading the definition again.
So x is a limit point.
So
If
0
every open set containing that point
minus
intersects A at a point other than x.
How does it intersect 0?
0, so now let's look at 0. So you want to see how is 0 a limit point?
Yeah.
Okay, that's nice. So 0. Here's 0. And we're going to put a really, really small interval around there.
There'll still be something in there.
Doesn't matter how small of an interval you place around there, I can always find a point still inside of here.
Oh, that's what's not empty. That's
Right.
your point. That's your whole point. I'm totally seeing it now. You're saying take away the neighborhood, or take away the point that you just created your neighborhood around, and you'll still find things in A.
Yes,
I see what you're saying.
that's it. That's exactly another way of saying it.
I know.
No, you're doing
I was
great.
looking at, yeah.
But take any open interval around 0 that you want. I don't care how far to the left it goes, but it's going to go some distance to the right, call it epsilon, right?
Right.
If it's an open interval. How many of you know the Archimedean property?
It sounds familiar, but
What's the Archimedean property?
Well, like, for any number you choose, you can always find a 1 over n smaller than that.
That's a more complicated version of it. It's a really simple idea. Archimedean property is there's no biggest number. That's it in a nutshell. The way we typically write it is for any number you pick, I can find a positive integer bigger. That's the simplest form, right? That's called the Archimedean property. So for any massive number you choose, I'll choose 1 over epsilon, since epsilon is going to be a really teeny number, but it doesn't matter. For any number you choose, 1 over epsilon, I'm writing up there, I can always find a natural number bigger. So this is a number, and I'm saying I can always find a natural number bigger. We're guaranteed that by the Archimedean property, right?
Right.
Well, that's equivalent to, which is what Emma was saying, 1 over n is less than epsilon. Times both sides by epsilon, divide both sides by n, you get this.
Right.
Follow the algebra there?
Yeah.
So then 1 over big N is less than epsilon. For some big N. So 1 over big N, whatever that big N is, might be 10,942,621. Depends on what the epsilon is. But for any epsilon you pick here, I'm guaranteed that there is some big number n, such that 1 over n is less than epsilon. So that big number n, whatever it is, 1 over n, I know is in here. So it doesn't matter how tiny of an interval you take around there, I can always find a 1 over n in there. Right? This 1 over n is going to be in A. A is the set of all of those. Here's a particular one. We found one. And is that 0?
Mm-hmm.
No, so we found one that's not 0.
Yeah.
Make sense?
Mm-hmm.
Those of you that took calculus, feeling a little bit like calculus there?
Yeah.
Yeah, that's basically what we do in calculus all the time. Well, early on. So we just did this. So we've got 1 over 1, 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, 1/8, etc. Take that set. What were its limit points? Just a set containing 0. This is the only point in R such that no matter how small of an interval you place around it, you're guaranteed to get one of these points in A. And since 0 is not in A, then the point you get won't be 0. So you'll get a point other than the limit point. Make sense?
Mm-hmm.
Okay. Let's do another one. So let's look at the open interval 0 to 1 closed, standard topology on R. What are the limit points of this set? You understand what this set is?
Yeah.
All the numbers greater than 0 and less than or equal to 1. Right?
Right. What are all the limits?
So what are the limit points of that?
0.
0's in there?
But
Yeah.
0's not in there. 0's not in there.
No matter how small of an interval you put around 0, will it intersect this thing?
Mm-hmm.
Yeah. Yes.
So 0's in there.
Right. But it's not.
So you found one of them.
But it's not. But it is.
Isn't one in there?
1? Yeah. No matter how small of an interval you take around 1, you'll intersect A.
Every
at some
point in there is a limit.
It's from 0 to 1, including 0 and 1.
0, 1, like that.
Okay.
Pick any point in here you want. Make as small an open interval around that point as you want. You're guaranteed to intersect this at some other point.
Right.
Make sense?
Yep.
Okay. Let's look at the set of all rational numbers in the standard topology on R.
It's R, isn't it?
R,
All rational numbers.
Because the rationals are dense in R.
because the rationals are dense in R. What does that mean? Besides Emma.
It means
Isn't R
it can
bigger
be
than the
infinitesimally
rationals?
small.
Isn't R what?
Bigger than the rationals.
Yeah, the rationals are a
Yeah.
subset of R.
So then I don't think it would be R.
So you don't think it's R, she thinks it's R. Any other ideas? Pick a random point that you know is not irrational and ask, is that a limit point?
Pi.
Yeah,
Pi. Is pi a limit point? How do we ask that? Create any small interval around pi that we want. Here's our number line, here's pi. Create any teeny tiny interval around pi that you want. Are you guaranteed to get a rational in there?
Yes, because they're dense.
No, he's just repeating Emma.
Well, they are. Well,
What does it mean to be dense?
means you can get infinitesimally small.
For any interval you choose, there's a rational inside it.
Perfect. One way to say it, the calculus way of saying it, is for any teeny interval a, b you choose, I'm guaranteed to always have a rational in there. That's what it means for the rationals to be dense. What it means in this class for a set to be dense is its closure equals the whole set you're defining a topology on. Right? A is dense if and only if A's closure is equal to X.
Yeah.
So Q's closure is equal to R. That's what it means for the rationals to be, for the rationals to be dense. But we don't really need that right now. All we need to know is that take any teeny tiny interval containing pi that you want. Every interval is guaranteed to contain a rational. Therefore, any small interval around pi is going to contain a rational. Since pi is irrational, then it's not in A. So it's going to contain a point other than pi in A. So pi is the limit point. So what are the limit points?
The rationals.
Huh?
Or
R.
R, yeah.
All of R. Every point is a limit point. For any point you pick, create a small interval around it, you're guaranteed to have infinitely many rationals in there.
Mm-hmm.
Does it make sense that you have infinitely many?
Yeah.
Because you have.
Once you have two rationals, you can generate infinitely many, right?
Right.
You just take their middle point, which is going to be rational, then the middle point two of those, which is going to be rational, then the middle point two of those, which is going to be rational. Okay. So that is what we mean by a limit point. I'll say it one more time, reading through the definition. Let A be a subset of a topological space X, then the point little x in big X is a limit point of A, provided that every neighborhood of X intersects A at a point other than X. Or X is a limit point if and only if, for every neighborhood of X, that neighborhood intersects A at a point other than X. Think you got it?
I think so.
Ready to move? Let's see what we're proving here. Let A be a subset of a topological space X. Okay, we're going to prove that the closure of A is equal to A union all its limit points. Understand what we're proving?
Mm-hmm.
And the way that I'm going to prove that these two sets are equal is I'm going to show the first is a subset of the second, and then the second is a subset of the first, therefore they're equal. So,
I thought in the beginning you said that A closure would just be equal to the limit points of A. Why is it now A and the union of the limit points of A?
this is in general. I said over here it happens to be the case.
Oh, okay.
So this is always true. Not just for our picture over there with the standard topology on R2. Okay. So now, let's see what I was saying. Oh, we're proving this. So we'll prove it this way first, why not? So let little x be any point in the closure of A, comma, and observe that if, let me think, take A in the closure, observe that if x is in A, then x is in A union its limit points. So pick x in the closure, and if the point that we picked is already in A, then we're done. So now let's assume it's in the closure, but not in A. Because remember, A is a subset of the closure, right?
Right.
So we randomly pick a point in here. I'm saying if it happened to be in here, then we're already done. We've shown it's in this. So now let's assume that we picked a point in here that's not in here. We're just handling two cases. You with me?
Yeah.
Okay.
2. Assume x is not in A. So it's in the closure, but it's not in A.
Right.
Let's see. Wonder if I even used that. We'll just prove it. Sorry, I'm thinking in my head and talking to you at the same time. It's not making sense. Just keep going. Okay, so now x is not in A, but we know that x is in the closure of A, right?
Mm-hmm.
And if x is in the closure of A, I don't know that I need to say this, but we'll say here, since x is in a closure, then what do we know about points in the closure of a set?
Theorem 2.5.
Theorem 2.5, the thing you memorized after last class, right? If x is in the closure of A, then for every open set containing x, it intersects A.
Well, that turned out to be really convenient.
Oh, and then x isn't in A, so it's going to intersect at a point other than x. Okay. So since x is in the closure of A, then for all use of x intersect A is not equal to the empty set. Since x is not in A, then for all use of x minus the set containing x intersected with A is still not an empty set. Right?
Mm-hmm.
So I know from Theorem 2.5 that every open set containing x intersects A at some point.
Mm-hmm.
Since x isn't in A, then the point that they intersect at can't be x.
Right. And you just wrote the definition of limit.
Therefore, x is in A prime, which gives us that A closure is a subset of A union A prime.
You wrote
You follow that? Should we do that one more time? Or do you got it? You need to just look at it? It's a lot of feedback.
Makes sense.
I'm good.
You good?
Yeah.
You're all good. Okay. 6. So now let's do it the other way. Now, comma, let x in A union A prime and observe that I don't know if we still need to specify this, but if x is in A, then we're done. And x is in the closure ring.
Mm-hmm.
Right?
Yep.
So now we just need to handle the case where x is in A prime.
Right.
You with me? Assume x is in A prime. But what does that give us?
Your definition of limit.
Then that gives me that
Wait.
for all u sub x intersects A is not empty.
Mm-hmm.
Don't you technically have to go to like u sub x minus the set containing x and then?
If getting rid of a point in this set
Yeah.
keeps the intersection empty, then we can keep it in there. Or if this intersection is not empty, then
I get what you're saying.
yeah.
I was just clarifying that that was the
We don't care right now whether or not they do or don't intersect at x anymore. You with me? Everyone understand this to this?
Mm-hmm.
If x is a limit point in A, then every open set containing x intersects A at some point. Right? We know at some point other than x, but still at some point. Why am I not bother specifying? Because I'm going to use what?
Theorem 2.5.
Theorem 2.5 again. What does Theorem 2.5 say? It says if for every open set containing x, it also intersects A, then that point is in the closure. So that gives me x is in the closure. Therefore, A union A prime is a subset of the closure, which gives me that A union A prime is equal to the closure. And we're done. Any questions on that? Anything weird? Anything confusing? Anything you need me explained? Just need to look at for a sec.
I'm ready to move on.
Alright. Gotta move the camera. You seem to help a little bit, so I'll do it again. Okay, I can see the whole thing. Alright, next. Looks longer. Quick corollary of this and something that we proved earlier. You'll see it all together here. Let A be a subset of topological space X, then A contains all its limit points if and only if it's closed.
Mm-hmm.
A contains all its limit points if and only if it's closed. Okay, so let's prove it real quick. So first, let's show if it's closed and it contains all its limit points, then we'll show if it contains all its limit points, it's closed. So 1, assume A is closed. Now if A is closed, it's equal to its closure. So then A is equal to its closure. We just proved any set's closure is equal to A union its limit points.
Yep.
So A is equal to A union its limit points, so it contains all its limit points, we're done. You see that?
Mm-hmm.
Alright, let's go the other way. Now assume A contains all its limit points. What does that mean? Well, that means A is equal to itself union its limit points. It contains all its limit points. But we just barely proved that that's equal to its closure, therefore A is equal to its closure, A is closed. Pretty straightforward?
Yeah.
Okay. Now, here's where I was afraid of losing you guys today. Sequences. So we're going back to definition 0.30, all the way back to preliminary stuff, to talk about the sequence. Now, a sequence is a special type of function, so first I want to make sure we still remember what a function is, right? Just high level, what's a function?
Some sort of relation.
It's a special type of relation
And one output, right?
where every input goes to unique output, or for every left-hand value we have a unique right-hand value. So it's a set of ordered pairs such that every left-hand value is paired with unique right-hand value. Make sense?
Mm-hmm.
That's what a function was. Now a sequence is a special type of function. A sequence is just a function whose domain is the positive integers. 1, 2, 3, 4, 5. So it's going to map 1 to something. It's going to map 2 to something. It's going to map 3 to something, 4 to something, 5 to something. And the thing it maps 1 to, we're going to call the first term in the sequence. And the thing it maps 2 to, we're going to call the second term in the sequence, etc. So let's look at the definition now and see if you just get it and I'm over-explaining. So given a set X, we're going to define a sequence on the set X. So given a set X, a function f from the positive integers to x. Anyone confused by this notation? F maps every positive integer to something in this set.
Okay.
That's what that's saying.
Okay.
Good? Nice little throwback. So given a set X, a function f from the positive integers to x is called a sequence on x. It's going to take a bunch of elements from x, and it's going to put one first, one second, one third, one fourth, one fifth, one sixth. And the one that comes first is the one that 1 maps to. The one that comes second is the one that 2 maps to. That's all we're doing, right? Okay. So, that's exactly what I'm writing here. So f, what is this going to look like? It's going to look like a function that maps 1 to something in x. It's going to map 2 to something in x. It's going to map 3 to something in x. It's going to map n to something in x. It's going to map, etc. There's infinite things in there. So there's infinitely many positive integers. So f is an infinite set.
Always. I guess.
Yes, because it has to map everything in here to something in here.
But
Now, there's no reason that x1 and x2 can't be the same thing.
Yeah.
Or that x2 and x3 can't be the same thing. That's perfectly fine. All we're saying when I say x1, I mean the first term in the sequence. When I say x2, I mean the second term in the sequence. Our sequence could be A, B, A, B, A, B, etc. Okay. So this is writing out the sequence when we think about it in terms of a function. Now obviously, x1 is whatever 1 goes to, so we have this shorthand way of writing out the sequence. Just x1, x2, da 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 da. For those of you from discrete math, what we mean by a list, that's a finite sequence. That's what a list is. Same thing. But anyways, so x1, x2, x da da da, xn. And then we even use this shorthand notation when we're talking about some generic sequence. For those of you in calculus, the way that we typically do a sequence was something like that. So you might have been used to seeing notation like that for a sequence. But same thing. Anyways, so that's a sequence. That's a generic sequence. Whenever you see xn in parentheses like this, what is this? This is a sequence on x, where the x of nth term is what n maps to. Let's look at a concrete example to help this all make sense. So now we're going to look at a specific sequence, f. It's a sequence on the real numbers. So it's a sequence of real numbers. By, what do you map n to? You map it to 1 over n. So what does 1 map to?
1.
1. What does 7 map to?
7.
What does 2000 map to?
1, 2000.
Correct. So you see how this is shorthand for an infinite sequence, right?
Mm-hmm.
And I'm just giving you the pattern for how you map each term. So this is shorthand for this, but we know that we can rewrite this like this, which is this. So this is how I would say, consider the sequence 1 over n. When I say consider the sequence 1 over n, that means 1 over 1, 2 over 2, or 1 over 2, 1 over 3, 1 over 4, etc. Feel like you're comfortable with sequence notation?
Mhm.
So when I use it in proof, I'm always going to just do it like this. xn for a sequence on x. That's what sequence is. Okay, so now we got a sequence. We can talk about a sequence converging, or the limit of a sequence. Probably good without the charger for the rest of class. Normally I'm going to stick this right in your face. So. Let's see. Perfect. Yeah, should be fine. Okay. So now, I had a good black marker and I left it over here. You can ignore the stuff over there. That's not for us. A convergence sequence. Oh yeah. Okay. So in a topological space, big X, a sequence xn in big X is said to converge to some point in X, provided that all neighborhoods u sub x of little x, provided that for all neighborhoods u sub x of little x, there exists a positive integer, big N, such that every term in the sequence is in that neighborhood from that big N onwards. This is dense. This takes forever for me to get through calculus students' heads.
We are
So-
literally just doing calculus all over again.
Yeah, it is. Early calculus can be viewed as just the analysis of the standard topology on the real numbers. Same exact thing. So this is identical. I mean, it's using some slightly different words, but this is identical to our definition for a convergent sequence in calculus. But we'll kind of hammer through it, try and use my picture ways of writing it better, and then come back and read it again.
Okay.
So we say intuition. Little x is what the sequence converges to. If it's the one number that the sequence keeps getting closer and closer and closer and closer and closer to. So intuition, 1 over n, that sequence, converges to 0. So the limit as n goes to infinity of this thing is 0. 0 is what the sequence keeps on getting closer and closer and closer to.
Yeah.
And it's the only number that the sequence keeps getting on closer and closer and closer to. Right? You might be tempted at first to think, well, isn't it also getting closer and closer to 1 over 1,000?
Well, you
No,
can get
you can
one.
go up.
Well, it starts out getting closer and closer and closer to that, but then it gets even smaller.
Mhm.
And it gets further and further away from that as time goes on. So 0 is the only term that it's always getting closer and closer to. So what we mean by that, then, is when you have 0 on the number line, reading this definition again, here's 0, here's our sequence. We're saying that this sequence converges to 0, means that for any neighborhood around 0 you choose, pick some neighborhood, some open interval, in the case of the standard topology on R, right? So we're saying for any neighborhood you pick, and if we were to map out the points of that sequence, they start out outside, but they get closer and closer, and eventually they start getting inside, right? And there comes a point in this sequence, that one was the first one, and from this one onwards, they were always inside, right?
Okay.
So that right there is our x sub big N. The big N is the index of that term. The big nth term, from that term onwards, we're always inside this neighborhood.
That makes sense.
So let's go back and read it one more time. In topological space X, obviously we're talking about R. A sequence xn, we're talking about 1 over n, is said to converge to 0 in R, provided that for any open interval around 0, there exists a positive integer big N, that's just the index in our sequence, inside of there, such that every term in our sequence is now inside that interval from big N onwards. Right? So if big N is 100, they were saying for x sub 100 and 101 and 102 and 103, from 100 onwards, all the terms of our sequence are inside this interval from x sub 100 onwards. Is that making sense?
Mhm.
So, converges to x provided that for all neighborhoods u sub x of little x, there exists some positive integer n, that's the index in the sequence, such that from that index onwards, we're always inside the neighborhood. And then we say x is the limit of the sequence, and we write that the limit as n goes to infinity of x sub n is equal to x. So now let's wrap our head around this, and then this is for calculus students to see how what they learned is the same. So what are we saying? We're saying that the limit as n goes to infinity of some sequence is equal to x is logically equivalent to, for every neighborhood of x, there is some index in the sequence such that every term in the sequence from that index onwards is in our neighborhood. Pick any neighborhood, I can find an index such that the sequence is inside that neighborhood from that index onwards. Make sense? When we think about it just with the standard topology on real numbers, it becomes this. So this is the one you see in calculus. So the limit as n goes to infinity of xn equals x is logically equivalent to, for any positive number, for any epsilon, this is what I'm going to use to create my interval around x. So for any length of interval you choose, not length, for any radius of interval you choose, even though it's a one-dimensional radius, for any radius of interval you choose, I can always find an index such that the sequence is in that interval from that index onwards. Right? And now they're not quite used to seeing it this way because there's another way to write this in terms of absolute values, and that's this. If xn is in here, that's logically equivalent to, the distance between xn and x is less than epsilon. Right? If xn's in this interval, then the distance from xn to x is less than epsilon.
Right.
Make sense? Because this is how we define the open ball around x, right? All the points whose distance is less than epsilon, and this is what an open ball in R looks like. Same thing. So, that's exactly what you see. This is the exact definition you see when you take a calculus course. And a lot of calculus is just looking at those exact limits.
X squared converge? I forgot.
Say that again.
Does x over x squared converge at 0?
Does x over x squared converge to 0? Yeah. So that's the same thing as 1 over x,
Oh yeah. Of course.
which we have written up there. Okay. So that is what it means for a sequence to converge to a point. And it's the limit of the sequence. It's one of the 4 big ideas in calculus. The big ideas in calculus are sequence convergence, continuity, differentiation, and integration. We'll cover converging sequences in this class, and we'll also cover what it means for a function to be continuous in this class.
Do you cover
And continuity is real easy in topology. Huh?
Do you cover divergence?
A divergent sequence?
Yeah.
I'm not sure the exact definition that they give a divergent sequence in calculus, because calculus you're limited to just the real numbers. The way that we've defined a converging sequence here, there's topologies where a sequence can converge to infinite number of numbers. It doesn't have to converge to just one number. That's just the case with what we call Hausdorff topologies, which the real numbers, the standard topology on the real numbers is Hausdorff. So we'll show that in that special topology, then they only converge to one number. I give you intuition for a topology where any sequence converges to anything. Let's do that one real quick. So I'll do the topology R. What's the topology I'll give it?
The rationals.
So here's my topological space. Here's my set. Here's my topology. Any sequence converges to any point. Because there's only one open neighborhood. Well, there's 2 open sets, but This is the only one that's going to be a neighborhood of any point. Pick any point you want, that's a real number. Here's all our open sets, therefore this is the only neighborhood of it. Therefore, every neighborhood of any number contains every number. Any neighborhood of any number contains every number. That's the right way to say it. So, in this topology, you pick any sequence you want, it converges to anything. So,
Which is divergent.
it's one of the reasons, gives you intuition for why that topology is often called the chaotic topology. Okay. Any questions here? Any clarification you want here? Or ready to move on to examples?
It'll be nice to see example.
Okay, yeah, we'll do an example real quick. Right here, we'll go over it. And then we can do more examples if you want. So doing a quick proof, a more topological proof than a calculus proof, but exact types of stuff you'd be doing in calculus. So we're going to prove that the limit as n goes to infinity of 1 over n is equal to 0 in the standard topology on R.
Okay.
And that one hopefully appeals to your intuition. Yeah, we already talked about it.
Yeah.
Yeah. So let U be any open set containing 0. What do we need to show? So if we're trying to show that this converges to 0, what do we need to show? We need to show that for any open set containing 0, I can always find an index in our sequence such that from that index onwards, our sequence is always inside that open set.
Yeah.
So we start out with any open set U that you want. My job now is to find an index that makes this true. Oh, sorry, up here. For any open set you give me, I need to show that I can find an index that makes this true. So U is some open set. My job now is to find the index n that makes this true, and then we're done.
Yeah.
Make sense? What our job is?
Mm-hmm.
Wonderful. So let U be any open set containing 0. And observe that, remember, we're in the standard topology on R. The standard topology on R is the union of one-dimensional open balls. Or in other words, open intervals. But I'm going to stick to using this open ball notation here to help you when we get to this proof. So in the standard topology on just R, an open ball is an interval, right? It's all the points within epsilon of 0.
Yeah.
Okay, so let U be any open set containing 0 and observe that, since we're in the standard topology on R, then there must exist some open ball containing 0 such that that open ball is a subset of U, not AB, of U, right? U is just a union of open balls. Since 0's in U, there must have been an open ball containing 0.
Okay.
With me? And just noting, this open ball is the exact same thing as this interval, negative epsilon to epsilon.
Yeah.
This open ball is all the points within epsilon of 0. All the points within epsilon of 0 are these points.
Okay.
So just trying to keep clear in your head. For this proof, we're just talking about a simple interval. Although this notation might look more complex than something as simple as that.
Makes no sense.
What?
All the points between epsilon and 0 are negative
I
epsilon.
think of 0 as the center.
No. This is, so let's write out explicitly what it is. So a ball centered at x with some radius r is equal to the set of all points y such that the distance from x to y is less than r. That's what it is generically. In our context, what does it mean? The ball centered at 0 with radius epsilon is equal to the set of all points y such that the distance in one dimension, you take the absolute value of the difference, such that the absolute value of y minus 0 is less than epsilon.
It's really simple if you just draw a picture of it. That second part is
Well,
simple.
I wasn't here for the ball lesson, but now I totally understand.
Watch the recordings. My wow.
I will.
You can watch them on double speed. You can get through 3 of them in 3 hours.
I am going to.
Okay, Anyways, okay, so now does it make sense to you that this and this are identical? Okay, good. Probably not bad that you didn't watch them, so you can make sure I explain everything good enough that makes sense. But go watch them. No, it is bad that you didn't watch them, period.
It's driving me to want to watch it, yes.
Okay. Anyways. So we know there must be some open ball containing 0 with some radius, we'll call it epsilon, such that that open ball is a subset of U. Right?
Mm-hmm.
Now do exactly what we did somewhere back there. By the Archimedean property, there exists some positive integer bigger than 1 over epsilon. 1 over epsilon is just a number. By the Archimedean property, I'm guaranteed that I can always find a positive integer bigger than any number you pick. Makes perfect sense, right?
Mm-hmm.
Okay. So, 1 over epsilon, that's just some number. I'm guaranteed I can find a positive integer bigger. And if I can find a big N bigger than 1 over epsilon, that's the exact same thing. Multiply both sides by epsilon, divide both sides by N. Notice epsilon's a positive number and N's a positive number, so our inequality stays the same. I flipped the inequality because I kept N on the same side. Probably shouldn't have done that. But now 1 over N is less than epsilon. Is anyone confused with this? Okay. And then 1 over N less than epsilon, that's the exact same thing as 1 over N is in this interval.
Okay.
Good?
Yeah.
Alright. Then, for any N bigger than 1 over N, notice if we take that N and we make it bigger, then that makes this number smaller.
Yeah.
As we make the N bigger, the whole number becomes smaller, we're getting closer to 0. Right?
Yeah.
So if 1 over N is in that interval, then if I make the N bigger, we're still for sure in the interval. You follow that logic?
Yes.
Okay. So then, for all N greater than or equal to that big N, 1 over little n, for all little n bigger than or equal to that thing, then all those little n are also in that interval. But that interval is a subset of U. So all those little n from that index onward are in U. I did it. I found the big N. I found a big, so you give me any U you want. I just barely found an index, big N, such that from that index onwards, all the terms in the sequence were in U.
Okay.
Anything weird?
Did you go over the Archimedean property in this class?
It's not something that you prove in this class. It's not something you prove in analysis, so I just gave it to you. That's
Was
the
that
case.
a prereq for this class?
No. No, it's not. But it's helpful if you've had it. The author of this textbook presupposes that you've done not necessarily real analysis, which is what I'm calling calculus here, but that you've done like a college Calc 1, Calc 2, Calc 3 type material.
In those classes, you would never.
In those classes, the textbook is going to throw out, this is the Archimedean property and give it to you real quick, but never expect you to use it. Maybe a couple problems, but then you go on your merry way. So it's something that chances are if you took a college Calc 1 course, you did come across the Archimedean property, but it was in no way stressed. You were never required to really understand it, so went in one ear out the other.
Right.
Anyways, so therefore the limit as n goes to infinity of 1 over n is equal to 0. Make sense?
Mm-hmm.
Okay. So that's how we prove that sequence converges into topology. So now let's do a nice little proof here. Let A be a subset of Rn. Remember what Rn is? R cross R n times. So if I do R1, that's just a real number line. R2, that's just a plane. R3, three-dimensional R. R4, can't imagine what it looks like, but it's just R crossed with itself 4 times. It's some space where you need 4 points or 4 numbers to signify a point instead of just 3 numbers. Doesn't matter. Okay. So let A be a subset of Rn in the standard topology. Remember how we defined the standard topology on Rn in general? It's any sets we can get from unions of open n-dimensional balls.
Yeah.
Does that make sense?
a little bit.
It's just like the other ones, right?
Yeah,
Except just with,
so it's still, all our balls xr is equal to the set of all y such that the distance from x to y is less than r. It's just our distance function changes depending on what r is, or what n is. If n is 1, our distance function, the distance from x to y in one-dimensional space, if you're okay with me calling it that, is equal to the square root of x1 minus x2 squared, which is exactly the absolute value of x1 minus x2, same thing. In two-dimensional space, it's just the Pythagorean theorem. The distance from x to y, not x2, y1. In this case, I'm using a 1 to signify its first coordinate, but in one-dimensional space, x only has one coordinate, and y only has one coordinate. In two-dimensional space, then the distance is the square root of x1 minus y1 squared plus x2 minus y2 squared. You remember deriving this using the Pythagorean theorem? And in 3 dimensions, you just add another one of those terms on. So for n dimensions, then it's just plus dot 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 plus x sub n minus y sub n squared. So depending on what that n is, it determines what distance function we're talking about. Once our distance function is determined, how we define our balls, always the same. So n just determines which distance function we use. Make sense?
Okay.
Okay. We already saw that. And back to our proof. Our proof. Okay. So now let A be a subset of Rn in the standard topology. So A is a union of open balls. And notice we don't really care if we're talking about one-dimensional, two-dimensional, whatever. We're just going to deal with open balls. All the points within some distance of some number, depending on where we center the ball. What are we going to prove? We're going to prove that if x is a limit point of A, then there exists a sequence that converges to that point. Make sense?
Okay.
Yeah.
Then there exists x, a sequence in A, I'm pretty sure. Because obviously there exists a sequence that converges to that point. Because we could just pick the sequence x, 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 x. So that's not very useful. What we mean is there exists a sequence in A. Because x might not be in A, just because it's a limit point doesn't mean it's in there. So there exists a sequence xn in A such that the limit as n goes to infinity of that sequence is equal to x. Make sense?
Mm-hmm.
All right. So, let's see. Let x be any point in A prime, comma, any point in A prime. Let's see, I'm going to have to construct my sequence. How do I want to say this? Maybe I'll start by making the balls. Well, I kind of need to say it. Since x is in A prime, I don't know how to say it, comma, then the ball centered at x with radius 1 over n intersects A. Well, I'll just write it out because I actually want to say different. So then the open ball centered at x with 1 over n as a radius intersects A at some point other than x, comma, call it xn 3
just confuse the sequence with the point.
of x ends from up there. So, sorry, I had to kind of write out a lot before I could put it all together. So I know that x is a limit point.
Yeah.
What does it mean for it to be a limit point? It means every open set containing it intersects A at a point other than x.
Mhm.
X is a limit point of A means every open set containing x intersects A at a point other than x. Right?
Mhm.
Now here's what I'm doing. I'm saying, look, I'm going to create a sequence here. So I'm going to look at a sequence of open balls. I'm going to look at the open balls centered at x with radius 1 over n. I'm going to do this for a radius of 1, a radius of 1/2, a radius of 1/3, a radius of 1/4, etc. But for each open ball centered at x with radius 1n, notice this is always an open set, right?
Yeah.
And it contains x. So this is always an open set containing x. Therefore, the ball always intersects A at a point other than x. I'm calling that point where this ball intersects A, xn.
Okay.
So x sub 1 is where the ball centered at x with radius 1 intersects A. X sub 2 is a point where the ball centered at x with radius 1/2 intersects A. Make sense how I'm defining my sequence?
Mhm.
Everyone good up to the point where I have my sequence? My sequence makes sense? And does it make sense that my sequence is in A?
Yeah.
Yeah, because it's a point where these open sets intersect A. So my sequence better be in A. So, for it remains to show that the limit as n goes to infinity of xn is equal to x. So I just barely constructed some sequence in A. Now I need to show that that sequence does in fact converge to x and we're done. Because that's what I was trying to prove. I was trying to prove that for any x that's a limit point, I can find a sequence that converges to it. I found a sequence, now I need to show that the sequence converges to it. What does it matter if I find some arbitrary sequence? So it makes sense what we're trying to do now?
Yeah.
Okay, so I'm trying to show that this converges to this. It's almost like a separate part now. So how do we show that a sequence converges? The exact same thing we did over here.
Find it.
I'm going to let U be any open set now containing x. I need to find an index big N in this sequence such that from that index onwards, my sequence is inside U.
Yeah.
Exact same process we did over there. And that's why I want to use the B's there to help you see the connections. Alright, so notice the parallels that we're going to follow now. Exact same thinking. Let U be any open set containing x and observe that there exists some open ball centered at x with some radius epsilon such that that open ball is a subset of U. U is an open set. U contains x.
Mhm.
We're in the standard topology. Therefore, U is a union of open balls. Since x is in U, there must have been some open ball containing x.
Yep.
Good so far?
Mhm.
Okay, so here's the open ball at x. And we know that there is one that's a subset of U. Now, we're going to use the Archimedean property. By Archimedean property, there exists some positive integer such that, kind of skip ahead now, 1 over n is less than epsilon. Right?
Yeah.
So,
Then for all n.
yeah. So we've got this same thing. Maybe make the same note here. That gives us that, well, how do I want to say that? Maybe we'll leave it there for a second. Maybe we're going to have to stray away a little bit. So, here's how I want to say it. So, such that that is less than that, comma, and observe. I'm trying to connect back up to my sequence to get you to see the connection. Observe x sub n is always in the ball centered at x with radius 1 over n by definition. I'm trying to throw back to our sequence. Remember how we defined our sequence. Our x sub big N term in our sequence was the point in A that intersected this ball.
Yeah.
So, x sub big N is definitely in that ball.
Okay.
Which now is a subset of bx epsilon. Right? If we make the radius smaller, we created a subset. It's a ball centered at x.
Yeah.
You follow that?
I think so.
These are all the points within epsilon of x. These are all the points within 1 over n of x. All the points within epsilon of x better also be within 1 over n of x. Other way.
Yeah.
All the points within 1 over n of x better be within epsilon of x. Let's use concrete numbers for a second to really help a quicker intuition in case it's not working. Let's pretend that that's 2 and that's 1.
Mm-hmm.
All the points within 1 of x better be within 2 of x.
Okay.
They're within a small distance of x, they're within a bigger distance of x. Otherwise we break the triangle inequality. Okay. Then, for all n greater than or equal to n, x sub n is in the ball centered at x with that as its radius is a subset of b sub x epsilon. You okay with that?
Yeah.
Because this line was true at big N.
Mm-hmm.
So it's also going to be true at big N plus 1, right? And at big N plus 2, and at big N plus 3, and at big N plus 4. And at all n, little n greater than or equal to big N. Then it's going to be true.
Yep.
Then x sub n is in U for all n greater than or equal to n. Therefore, the limit as n goes to infinity of x sub n is equal to x. And we're done. Any questions there? I think we're past the hard part. Everything makes sense now, right?
I think so.
Perfect. Okay, so we just really showed that in the standard topology, a point being a limit point of a set is the same thing as there exists a sequence that converges to that point in the set. So this is the set of all, another way to think about it is this is now the set of all points that we can find a sequence in A that converges. Take a sequence in A that converges, the point it converges to is now a limit point of A. That's another way to say it.
Okay.
Sorry, trying to come up with different ways to say the same thing. Okay, and moving on to our last theorem. So I told you that just because a sequence converges to a point does not mean it converges to just one point. which kind of goes against our intuition a little bit for what we want. Like when we looked at the sequence 1 over n, it only went to 1 point. It can only be getting closer and closer to 1 point. Turns out that's only true in a Hausdorff topology. And so that's all you need to require is that a topological space is Hausdorff to be good. For Jake, in case he didn't get Hausdorff, what does it mean for a topological space to be Hausdorff? Hausdorff.
Yeah.
So if I have 2 points,
Neighborhoods.
what?
Then they do not intersect each other.
2 points don't intersect each other?
No, they're neighborhoods around.
There exist 2 neighborhoods, 2 open sets containing those points that don't intersect.
Yeah.
They're housed off. They have their own neighborhoods. Hausdorff.
I'm sure.
Can't believe you guys don't remember that. That's the one I remember. No matter how much time's gone by since I've done topology, I always remember
Just the
Hausdorff.
last name of some dude.
Just get the
It is.
A over it.
Separate neighborhoods. They're housed off. Okay. So if X is a Hausdorff space, topological space, then every convergent sequence in X converges to a unique point. So let's go. 1. Let X be Hausdorff, and let Xn in X such that Xn converges. So big X is some Hausdorff topological space, and Xn is some sequence that converges. That's all we know about it. We need to prove that it only converges to one thing. How should we do this?
XN isn't necessarily in the neighborhood.
We haven't talked about any neighborhood yet.
The Hausdorff neighborhood.
X, so here's X. Some set with a Hausdorff topology. What does it mean that X has a Hausdorff topology? It means pick any 2 points in X you want. I pick this point and this point. Then there exists 2 open sets I can create around those points, such that the open sets don't intersect.
For every point in the Hausdorff.
For any 2 points you pick
In the whole Hausdorff.
in all of X, in the whole set.
Okay. That makes
Hausdorff is a property of a topological space. So I have some topological space X. It's Hausdorff if and only if, for any 2 points I pick, I can find open neighborhoods, I can find open sets containing those points that don't intersect. Or I can find neighborhoods containing those points that don't intersect. Okay. Anyways, so we're trying to prove that it can only converge to 1 point. How would we prove it only converges to 1?
You use
Assume that there's 2.
Assume, by way of contradiction, it converges to 2, and so that leads to some contradiction. 2. Assume, by way of contradiction, that the limit as n goes to infinity of xn is equal to a, and the limit as n goes to infinity of xn is equal to b, where a and b are not the same point, right? Now, let's get intuition for why Hausdorff is enough for us to say this has to converge to one thing. So here's our topological space, here's A, here's B, they're distinct points. Now I'm saying I can find some sequence that gets closer and closer to A, and at the same time gets closer and closer to B. Why isn't that going to work? Because I can find some open set around A such that the sequence is always in here from some point onwards, and I can find some open set around B such that the sequence is always in here from some point onwards. Impossible picture. Because the sequence can't be in 2 places at once from some point onwards, because these 2 sets have no overlap.
Okay.
That's a big picture how we're going to attack this. So, let's write it out. So I have A and B are 2 points in X. They're not the same point. Therefore, there exists 2 neighborhoods that are disjoint containing them. So since X is Hausdorff, then there exists U sub A and U sub B, neighborhood of A and neighborhood of B such that U sub A intersect U sub B is equal to the empty set. They have no points in common.
Mm-hmm.
4. Since the limit as n goes to infinity of x sub n is equal to A, comma, then there must be some index, call it n sub A, I guess. That looks too much like sodium. That's gonna mess with my brain. N sub 0, I'll call it. Since the limit as n goes to infinity of x sub n is equal to A, then there must exist some positive integer such that x sub n is in U sub A for all n greater than or equal to n sub 0. Right? That's what it means for xn to converge to A. If xn converges to A, then that means for any open set you choose containing A, I can find an index in the sequence such that the sequence is always within that open set from that index onwards. So for any open set you choose, for any open set, U sub A, I can find an index, n naught, such that from that index onwards, my sequence is always inside U sub A.
Yeah.
That's what it means for the sequence to converge to A. The exact same thing for the sequence to converge to B. 5. Since the limit as n goes to infinity of x sub n is equal to b, then there must exist some index, call it n sub 1 in z, the positive integers, such that x sub n is in U sub b from that index onwards. Right?
Yeah.
6. Let big N equal the max of n sub 0 and n sub 1. Then x sub n is in U sub A and x sub n is in U sub b for all n greater than or equal to big N. If this is true from n0 onwards, and this is true from n1 onwards, and n is the biggest of those two, then both these are true from n onwards.
Right.
Okay.
Make sense? So, both those are true for all n greater than or equal to n. Contradiction. Big contradiction. Whoa! Why is that a contradiction?
Like I
Is
can
there
see the picture
disjoint
still, but
neighborhoods?
I know that these two are disjoint. Their intersection's empty. And I just found infinitely many points in both of them.
and you just found out there's infinitely points that they share.
Yeah,
Right.
because all these xn's are in U sub A and they're in U sub B. So it's in the intersection, right? Maybe I should have written that different. Xn is in U sub A intersect U sub B for all n greater than or equal to n. Maybe that makes it more obvious.
Yeah, that helps.
And maybe even, which is not equal then to the empty set. Maybe really throw an exclamation point out there. Right? Contradiction, therefore our assumption that there's 2 is wrong, therefore there's not 2. Okay, so how do we prove that there's not 3 points that it can converge to?
Well, it's like the same process, is it not?
If there's not 2, then there can't be
Yeah.
3, because to be 3 there has to be 2. So we've already handled 3. We've handled all ones greater than 2 or more. But how do we know that it can't converge to 0 points?
Because there's a neighborhood.
It doesn't make sense to talk about a sequence that converges that doesn't converge to anything. So the fact that it converges guarantees us that there's 1. We just barely showed that there's not 2. So there's 1 and only 1.
Okay.
So we don't need to add anything. I just want to make sure you understood how we now know that every sequence that converges to a unique point.
In
Follow the logic there?
Hausdorff.
Yeah, if the topological space is Hausdorff, then every sequence in it converges to one and only one point.
But if it's not Hausdorff, then there can be two.
Yes.
There are topological spaces where a sequence, the same sequence, converges to more than one point. For example, we already talked about this one, but we'll write it up there again. If I use a topological space, R with the topology, the empty set in R. So here's my set, here's my topology.
Okay.
Every sequence converges to every number. So in this topology, the limit as n goes to infinity of 1 over n is equal to 27. It's true. For every neighborhood containing 27, let's look at all our open sets. Here's all our open sets. The only neighborhood of 27 is all of R.
Okay.
There you go. So for every open neighborhood, or for every neighborhood of 27, I can find an index, namely the first index, such that that sequence is in that neighborhood from that index onwards. The sequence is always in there, so it's in there from 1 onwards. So the sequence converges to 27.
That's messed up.
Which is why, well, I don't know if it's why, but one of the names for this topology is the chaotic topology.
Okay.
Every sequence converges. Every sequence that converges, well, every sequence does converge, and every sequence converges to everything. Yep, messy, messy. Not as nice as just a nice simple Hausdorff. And think about how little structure we had to give our topology to make so that convergent sequences now act all nice the way that we want them to. There's still tons of stuff that we haven't assumed yet, like we don't know anything about distances in this topology. So we're not saying that it gets closer and closer and closer and that the distance between is getting smaller and smaller and smaller, because we don't have distance in this topology. All we know about this topology is it's Hausdorff. That's it. That's all we know.
Right.
And that was enough to define convergence.
Interesting.
So, well, we can define convergence on any topological space, but this was enough to have convergence start acting the way we want convergence to converge to just a single point. And that's all the structure we need. Just topological space, it's Hausdorff. Now you have convergence acting the way you want. So that's what we're doing with topology over and over again, and maybe I ought to point it out more often than I do, is we're getting these concepts, these relatively high-level concepts that are used in a lot more structured ways, and we're just coming up with the very minimum structure we need to still get that notion, to still capture that idea. And so this is the minimum notion that we needed for a convergent sequence, and then over here is a minimum notion that we needed for a convergent sequence that converges to a single point. And we're still a long ways from talking about all the nice properties that you have on the real numbers when you're doing something like calculus.
Right. That's cool.
Yeah, it is cool. It's one of the reasons that I love topology so much is it's very minimal. It's the minimal structures that you need for certain things. And when we talk about continuous functions, that's the craziest one. Well, I don't know how to say that. I think it's the craziest one. How simple it is to talk about continuity here versus when you go compare it to the epsilon delta definition that you're given in calculus.
Yeah, that one. Sloppy.
Anyways, so that's that. That's the end of lecture. We can turn off the camera. Well, do you have any questions that you want recorded first? No? We're running out of time.